So we're looking at differential equations today. So we have actually dealt with differential equations before. Basically, we're given the derivative, and we're asked to integrate. Okay, so you're basically asked to find the antiderivative. And we're just going to break down the process of what we've actually been doing, and we're going to apply this to something a little bit more complicated. So here we have dy by dx, and if we want the original equation y, what we do is do this. So here's our derivative. So the derivative function is 2e to the x. So in essence, we're being asked to anti-differentiate this. Okay, so we want to find the antiderivative of this, which is just basically itself. However, what we want to do then is the process of doing this is actually doing this. So we want to split up the dx and bring it to that side. So if you've ever wondered why that dx is an integral, it's because really what we're doing is putting it onto that side. And what we're doing is using the height of the derivative function, and we're multiplying it by the width, okay, the little change in x. And that gives us the change in y, okay, the change in the displacement on the original graph. So there's our area function. There's a little bit of area that we find, and it's related to the fundamental theorem of calculus. It's a displacement or a small change in the antiderivative function. And what we then do is we take that little bit of dy and we sum them all up and we get y. And on the other side we do the same thing. We sum them all up and essentially we get that. Okay, so that's how what we've actually been doing. We've been kind of skipping all these steps in between. We've just been saying from here anti-differentiate. Okay, we're going to use the integral and then find y by that method. But again, we're just going to start then using this more formal process, and we're going to apply this formal process in a slightly different context. So here's my dx. It's going to go with my x's here, so I then end up with dy. Okay, I'll write that a little bit nicer. Our dy is equal to, and we get our 1 over x. I'll choose a proper color here. We get 1 over x plus 2x, whatever that is. I'm going to multiply that derivative by dx. So in essence, what I've generated is the height times the width, and that equals the small change in the antiderivative. And from here, I'm going to integrate this. I'm going to sum up. Integrating means to sum up those areas. Okay, so I'm going to integrate that as well. Oh, what happened to my... Okay, so I'm going to sum up this side as well. Okay, and then what I end up with then is y equals the integral or antiderivative of the derivative function. Okay, and then that becomes log x plus x squared plus c. Okay, so there we go. So there's my general solution to this differential equation. So this slope equation comes from this original antiderivative function. Okay, so that's kind of just more formal process of what we've been doing already. So same thing here. I'm going to split up my variables. Okay, I'm going to put the dx to this side and integrate both sides and find the antiderivative of this. Now, if this is my differential equation, I want the equation that goes through a specific point. It goes to this point 0, 1. And by doing that, what it allows me to do is then, instead of having some general solution, I can solve for the c, and I can find the specific solution, the specific function y that has this slope and goes through this point. Okay, so I'm going to do what I did before. So I have my dy by dx. Okay, so here's my dy by dx. So this is a slope equation. And what's implied is I want to solve for the antiderivative. I want to find the original y. So there's my slope equation. I'm going to split up my variables. So I'm going to put the dx on this side. So in essence, I'm taking the height of the derivative times the width, which is my Riemann sum bar. I'm going to sum up both sides of that. I end up with y on this side, and then I'm going to anti-differentiate this side. So I get sine x plus c. So this is what we call the general solution to this differential equation. So a whole bunch of lines that have this form have slopes that are generated by this formula. Now, I want a specific one. I don't want just any line that goes through that has this shape. I want the one that goes to this specific point. So I'm going to plug in my y and x, and that allows me to solve for c. Okay, so c is equal to 1. So then the specific, so this is my general solution here to this differential equation. My specific solution that goes through that point is going to be y equals sine x plus 1. Okay, there's the specific solution that goes through that particular point.